Powerful collaborations, cutting-edge science, and curious minds coming together for a glimpse of the future. Stay tuned as we look at the latest updates on some of the most promising technology projects. In this episode, we look at the Car2TERA project. This is a new effort to push the automated vehicle a little closer to reality through the use of advanced radar. But what's needed before we can actually let go of the steering wheel? Hello and welcome. I'm Peter Ballant, and today we are in the Technicon studios speaking with Joachim Oberhammer. He's the scientific lead for a new project called Car2TERA, which looks at using sub-terahertz frequencies for self-driving vehicles. Welcome to our studio.
Thank you very much.
And the first question I have for you is, can you give us just the overview of this project, Car2TERA?
So this is a recently started European project. So it's funded by the European Commission, and it involves several countries in Europe. And the main focus of this is to utilize state-of-the-art terahertz technology. So that's electronic technology which is utilizing the terahertz frequency spectrum, which is 100 times higher frequencies than mobile phones, for instance. And we want to utilize this frequency spectrum with recent technology to create a new car radar sensor, which is for passenger safety in the cabin of the car, so monitoring the passengers in the pre-crash and post-crash scenarios. And the second track in this project is also on creating new high-frequency technology for wired communication links, and this is mainly in base stations for mobile phones, and where there's a currently bottleneck in how to interconnect these base stations. And that technology should be able to boost 5G and beyond 5G telecommunication systems.
You mentioned radar systems, and you say you're looking at developing radar systems. And I'm thinking, okay, my car has a radar. When somebody's in my blind spot, it tells me. Is today's technology just not good enough, or does it need something different?
So there are different types of radars which are used in cars nowadays. And as you mentioned, you have the forward-looking radar, which is for crash or detecting obstacles in front of the car, and then you have the sidewards and the corner radars. And this is a completely new radar sensor application in the car scenario. So this doesn't exist at the moment. So there are no comparable radar sensors yet. So this would be a radar which is inside the car, monitoring the positions and the behavior of different parts of the bodies of the passengers, mainly in a crash scenario of the car. And currently, for this application, there's cameras being used, but cameras totally fail, because in a crash scenario, you have within milliseconds, you have to take decisions. So the car has to take decisions which kind of airbag to inflate, and cameras are too slow for that. And also cameras don't have the necessary contrast, like if there's strong sunlight or if it's very dark. So right now, automotive car manufacturers are looking for alternative sensors here. And here, a high-resolution radar could be a solution. And that's the reason why there's interest in using a new radar sensor, which is operating at much, much higher frequencies than conventional car radars. Because with much, much higher frequencies, you have much higher resolution to resolve the situation inside the car. So this is for improving situational awareness of what happens in the car, and then to take measures for minimizing the injuries to passengers in the cabin.
So it's safe to say that these radars, these cabin monitors, they look to see what's happening, and if there's an airbag requirement, it looks to see which airbag to deploy first and then create a sequence.
Yes, like for instance, if the car knows how the head is moving during the crash, depending on that, the sequence of inflating different airbags, because it can be a sequence of airbags, not only a single one, that the sequence of airbag can be controlled by knowing how different body parts are moving. And this is even more important in future scenarios, like when you think about autonomous driving, because then the passengers will sit in the car, not being attentive to what happens. Right now, a driver is very attentive and see what happens. But in the future, people might be almost like lying around in the car or reading books. So then it's very important for the car to know where are the passengers, what are they doing, how are their body parts moving if a crash scenario happens.
Okay. And what is it about the terahertz frequency that makes it especially suitable for this application?
So conventional radars, in particular car radars, have a quite a low resolution, like it's even centimeters or worse than centimeters resolution. And that's enough to look whether another car is in front of you at 100-meter distance. So it's also enough to detect whether a car is approaching from the side. There could be a side crash. So it's good for external radars. But for internal in-cabin monitoring, you need much higher resolution because you want to be able to distinguish. You want to see the head, for instance. I want to detect how the different limbs are moving of the body. So you need much higher resolution. And for that, in principle, you have to go to higher frequencies to get higher resolution. And in the future, this could be even thought of detecting like the directions in which the passengers are looking, for instance. And for that, you need very, very high resolution radar.
And with this high resolution terahertz wave, what other uses do you have for this?
Well, currently, terahertz technology is mainly used for like radio astronomy applications. It's used for environmental sensing, like there are Sub-Terahertz sensors in satellites who are monitoring clouds and ice developing in clouds. So this is for weather surveillance, also for pollution monitoring, so for measuring air qualities. So terahertz technology is used for that. There's also medical applications for terahertz technology. There is also telecommunications very interested in going to terahertz technology because you have very, very large bandwidth, so you can have huge data rates going over terahertz frequency. So there's a lot of applications which really would need this frequency spectrum, but technology is not mature enough. So that's a key point in this project. We are developing next generation terahertz technology and using also industrial grade electronics for that. So it's not only a research focus itself, but we are trying to use industrial grade processes for that there can really be a quick commercialization of utilizing this technology.
So in this project, the Car2TERA project, are you making anything? Are you designing something? Are you making a prototype of something?
Yes, we are making 2 different prototypes in this project, and one will be this car radar sensor, so this in-cabin car radar sensor that we are prototype, and that will be developed together with an automotive system supplier, which is Veoneer. That's one, and the primary prototype. And there's also a secondary prototype, and that is together with Ericsson, and that is about routing terahertz signals over plastic wires. That's similar to a glass fiber network, which people might have at home nowadays. But it has a very large bandwidth, and it's low cost also, and is much more robust because the glass fiber connections are very prone to have problems with dust particles, for instance. So there's a very big reliability issues, and this terahertz over plastic fibers might solve a lot of problems and make the interconnections in base stations much more cost efficient and also more reliable.
Okay. How would you position this project technologically worldwide?
So basically there are different aspects, different technology building blocks which are put together in this project. And some of them are very, very cutting edge technology. So like we are using a silicon micro-machined platform technology for that. And there is only a few players in the world who can do that at the moment. And then another interesting aspect here is that we are trying to use silicon germanium semiconductor technology in that project. And here we are using industrial grade semiconductors. So And that is actually quite challenging to utilize this industrial grade technology at these very high frequencies. So from that point of view, I think this might even be the first project attempting to do that. So there are several aspects which are really this project is worldwide giving new directions.
You had a kickoff meeting today to start this project. How do you feel about that?
Yeah, it was very interesting to meet all the partners and to see the motivation in the eyes of all the people. So that was very nice. So this was a very good consortium, and people seemed to be very eager and engaged in the project. And of course, we also discussed technical issues. So there's a couple of critical points in the project which might fail, which need special attention. And these points were discussed, and where there were actions taken for how do we tackle the project, and how do we get started in a very smooth and efficient way.
What does success look like in this project?
Well, success here would mean that the industrial end users in the project, and that's Veoneer, the automotive system supplier, and also Ericsson, the telecommunication system supplier, if they would, in the end of the project, be happy with the prototype and utilize them in their next generation products, for instance, and see, okay, this technology which we want to use, which makes sense for us, and we can go on to industrialize that. I think that would be the main success in the project. Of course, for us, I'm from an academic academic environment. Of course, we are looking forward to doing very interesting publications, which will get a very high impact in the scientific community.
Okay. Now, I read quite a bit about technical readiness levels in the project summary. Can you tell us what that means?
Yes, so this is a scale basically on which different technology levels, like from very, very basic research to over prototypes, like proof of concept prototypes and industrial demonstrators, and finally towards products. So where do you place the state of development in a certain technology? And this project is characterized or classified as TRL, so Technology Readiness Level 4, which is kind of quite high actually for this type of project, I would say. So this is clearly a bit more than just a proof of concept. So it's going a bit closer towards industrially usable prototypes. So it's also this radar sensor actually is intended to be used in a mock-up cabin, in a car cabin at a car safety equipment manufacturer. So it's more than just a university laboratory demonstrator. And it's very challenging, of course, here, but I hope we can manage that.
I know you're not from the automotive industry, but based on what you know and your experience working in this field a little bit, where do you see cars in 10 or 15 years?
Well, cars will take over more and more functions from the driver. So we already have now a lot of car assistance function, and that can be a brake assistance or stop and go assistant. It can even be electronic stabilization program. So the car is kind of guiding the driver more and more, and this path will clearly continue in the future. So the final goal is, of course, complete autonomous driving, which might be very far in the future, not only for technological reasons, but also for liabilities or for legal reasons. So there are several reasons why this autonomous driving is not that easy to implement. So there's a long road towards that, but clearly along that way, there will be more and more functions which the car can take over or assist the driver, and also take more and more responsibilities from the driver to safeguard the driver mainly, and to also, of course, to make driving as a more pleasant experience.
Now, you also just finished up a project not so long ago called H2020, which also, again, looked at utilizing sub-terahertz frequencies. Is there anything from H2020 that you were able to exploit or that you will exploit? Can you bring over lessons learned from H2020 to Car2TERA?
Yes, that we can very clearly. And basically M3Terra was a project which was utilizing also a micro machine technology platform, which is also the center of this Car2TERA project. We were at slightly lower frequencies, which made it easier. And also the demonstrator was at a lower technology readiness level. So basically the Car2TERA project is more ambitious, both when it comes to frequencies, when it comes to the readiness level, so comes closer to actually an industrial demonstrator, and also complexity of the system itself. So basically I would say if we would not have had the M3Terra project before, it would be very, very difficult to go into this Car2TERA project. And the other thing is also, we learned not only technology in M3Terra, but we also learned how to manage these complex projects, because there's a lot of different technologies which have to be combined, and people are speaking different languages. There are different interfaces which were not clearly defined from the beginning. So there were also a lot of technical management issues in M3Terra, a lot of things which we forgot when we wrote a project plan, or we were not aware of critical points, a lot of risks which we did not estimate to that level before. And with that, of course, we go in with a completely different understanding, both from a technology point of view and from a management point of view, into this new project.
And I think it was you that said one of the biggest challenges was managing expectations in industry and managing expectations in academia, that these are two different playing fields, if you will, and perhaps a challenge in moving a project forward.
Yeah, there can be, of course, a clash of interest here between academics and industry, though actually I never experienced that in this project, neither in M3Terra, no, I don't expect it in Car2TERA either. So that's actually nice with this consortium, that really everyone in this consortium is kind of playing, rowing the same boat towards the same common goal. People are really working together on the common goals. So I definitely don't see here a clash of interests between academic or industrial partners, or between different industrial partners in the project.
Can you tell us briefly a little bit about your partners in this project?
So there are several partners involved in the project, and we have several large-scale companies, and that's Veoneer in Sweden is one of the world's largest automotive safety equipment providers. So that's the end user for this car radar application. Then we have also Ericsson involved. Ericsson is one of the world's 3 largest telecommunication systems and service providers. And that's a secondary end user in this project. We also have Infineon involved. So Infineon is one of the largest semiconductor manufacturers, and also micromachining, so for microelectromechanical systems manufacturer in the world. So these are the 3 big companies, and they are augmented by smaller companies, by SMEs. And here we have Anderal. It's a company in Spain who is focusing on antenna design. And we have ENT in Poland, who is providing graphene material. So that's a new type of material for this project. And we have Technikon in Austria, who is the coordinator of this project. It's a professional project management company, which is needed nowadays to run this kind of projects. And then we have the academic partners providing the state-of-the-art technology, and that's Chalmers in Sweden doing the integrated circuit designs, and KTH in Stockholm, also Sweden, from where I'm from, who is providing this micro-machine integration platform for this project.
And tell us your background. What's your day-to-day work like?
Well, I'm professor in microwave and terahertz microsystems at KTH, Royal Institute of Technology in Stockholm, Sweden. And yeah, we are working in frequency ranges nowadays from 100 gigahertz to 1 terahertz for different applications, telecommunication, radar applications, also radio astronomy applications, some medical applications, like we have done skin cancer sensor based on Terahertz technology some time ago. So we are trying to exploit new applications in the Sub-Terahertz frequency spectrum by using micromachining technology.
Is there anything else you can add?
Not really. So I think I'm looking forward to have a very interesting project with interesting results and satisfied partners, in particular the industrial end users. And I, of course, would like to acknowledge the funding which we received from the European Commission for this project. So it's actually very great research funding infrastructure in Europe available, which makes it possible to tackle these big technological challenges. And it's several million euros which are used in this project to develop this new technology. And so I would like to acknowledge that. And I hope we can make the best out of the taxpayers' money, and the taxpayers putting trust in us basically by giving us this money. And I hope we can make the best out of it.
How long is this project?
The project is scheduled for 39 months, and that's a bit more than 3 years. Typically, a project of this scale is scheduled for 3 years, and we already from the beginning asked for a slightly longer time because there are a lot of technical details which need to be timed properly, and it could take some time. So we hope to complete this year in 3 years and 3 months.
Thank you for speaking with us today, and thank you also for your contributions to this project, and we wish you much success for the project and for your team, and we'll talk to you again in a few months and see how you're doing.
Thank you very much.
This podcast has been brought to you by Technicon. The Car2TERA project has received funding from the European Union's Horizon 2020 Research and Innovation Program under Grant Agreement number 824962.